Right. We'll continue with the lecture about math models. Especially, you want to understand what it really means by abstraction function. And this is the topic for your lab number 2. So today is going to be relevant. Okay. Of course, the example we do in the class might be slightly simpler than what you have to do in lab 2, but just to give you enough idea and the principles. Let me remind you about a working example for the lecture. We're going to do a slightly more complicated one called birthday book, maybe towards the end of the class. We'll get there, and possibly to continue next Monday. But for today, we'll definitely finish the stack and finish all the principles. Let me remind you quickly. We want to implement stack, last in, first out, and we got 3 different strategies for implementation. Number 1 is going to be the end of the array being the top. Strategy number 2, the front of the linked list will be the top. And strategy number 3, the end of the linked list will be the top. Okay, just keep in mind. I'm going to keep reminding you. Of course, depending on which strategy you might have chosen, you may have to implement them differently, right? That's something we went through last time. But now we want to pay more attention about the overall design and see why it might violate certain design principles. That's something we want to see. Okay? Let me remind you one more thing before I go to the 2 design principles I would like to introduce to you in this lecture. This is basically something we went over last time about how you can write a postcondition over here. Let me do a little bit of remarks over here as a review. If you look at the postcondition for push, okay, especially if you look at the unchanged part over here, you can see the unchanged here, the second one. Apparently, we're using a cross loop. But the way we write this across loop is very depending on that particular strategy number 1, because the end of the array is actually the top of the stack. Okay, that's something you can refer to the lecture from Monday. But I'm going to talk about another contract just to do another exercise with you. Okay, we got push and we got pop. So here's my question for you. Okay. Every time when you want to judge to see whether your design is actually a good design or appropriate, think about what changes you might introduce to your design. And a very typical change is the change on the implementation strategy by the supplier. Let's say the following. If you, I don't have a line number, sorry. Look at this line here. At the moment, implementation is declared of type array, okay? And the end of the array is the top of the stack. Let me say the following change for you. If I change the type of the imp from array into linked list, number 1. Number 2, rather than the end of the array should be the top, now I want the front of the linked list to be the top. So here's my question. If I did that change, would I have to modify anything else in my code? Well, for sure, one thing you have to do is you cannot do force anymore, right? You got to do extend or maybe to insert to the front, whatever, okay? I'm not talking about implementation. I want to know about ensure. Any part I need to change? For example, can I still do this? If I change from array into linked list, can I use the indexing notation for linked list? Apparently I can, so syntactically that's not a problem. But what about the contract itself? Is it correct? Well, is it? Remember, for strategy number 2, we want the front of the list to be the top. So in that case, is it correct if I say imp at the end is actually G? That's apparently not right. So we should say imp at position 1, assuming that indices start with 1. Jordan, question.
Sorry, I'm just wondering, is count like defined elsewhere?
Good question. Jordan's question was about the count. That's something I didn't really put into the slides, but I can assume that count is going to be the stack size. Yeah. Just assume it's declared elsewhere. Yeah. Okay, so now apparently this one has to be changed, right? Because now the front of the list should be the top of the stack. So you should really change, for example, from count to 1. That's one change. And as soon as you do this change, that means you're modifying the interface or the popular interface of your stack class. Remember, all the potential clients of your stack class, all they look at is not the implementation. They look at the contracts, the precondition, the postcondition. So now, just by changing the implementation for the supplier secretly from array into linked list, you have to modify this which is the interface for the clients. So that's not a good design. Okay, you see what I mean? Guys, it's really important to understand. So let me just illustrate very quickly. Okay, what I'm trying to say is this. Imagine that we got our class over here. Okay, our class called stack. Okay, stack over here, of course, is generic. We'll talk about generic parameter after the math models, but for now, just put a generic parameter here. And then the implementation over here is going to be an array of some generic element here. Okay, and then of course that should be private. Let me ignore that detail for now. And then let's say for top, just one example. Top is going to return whatever element it is in the stack at the top. And then if I look at the interface, and postcondition is part of the interface, I would say result, the return value from this query here, should be the same as imp add position count. Okay, that's strategy number one. Okay, let me remind you, end of array is the top. That is why I'm using count over here, right? That's basically version 1. Now, I want to illustrate this is not a very good design because now if I change the type, let me do the change in red. Now I want to change the type into linked list. And then the meaning of the top is going to be the front of my linked list is the top, right? I'm changing the secrets for the supplier, basically, the implementation strategy. So now I was asking you, should I modify this? Of course I should. Now I should change that to 1. So now somehow your clients are really much bothered by the change of the supplier's implementation strategy, which they should not be concerned about. Okay, that's the issue for the design. Any question about this? We okay? All right. That's something you should really keep in mind every time if there's something that should be secret to the supplier. If you modify it, the clients should not be affected. If it's affected, then it's not a good design. And I'll get back to the design principle in just a moment. Let me just, so that's the version 1. We went through it. What I want you to really study carefully is the second version, which is more interesting contract you can write. Let's say for version number 2, which we just talked about, right? So now I changed the implementation into linked list. So now the front of the list is the top of the stack, okay, rather than the end. And then for the push, I can, first of all, the implementation, I should use proof front as opposed to using a force or whatever array-related features. And then in short, you can see now it should be imp.first as opposed to at the end, right? That's one change. What about the post condition here? Has there been a change over here? If you compare the two versions over here, okay, let me just try to swap it in between. You can see the unchanged. Let me just switch to my iPad here, and I will show it to you. Let's just talk about push as an example. Okay, so now this is strategy number 1. Okay, you can see for strategy number 1, we somehow say across, and then from 1 until count minus 1, right? On the other hand, for strategy number 2, we're changing the strategy. If we did that, in that case, in order for you to specify this particular post condition, so now you can see we are writing that differently. First of all, notice that it's different. So that means we are modifying the interface, the public view. But how do we actually write that post condition? Okay, let me give you a little bit insight into it, and then you can do the exercise. So expect we might ask you something later, like this. Let's say for strategy number 2, okay, just help you think about it. Okay, strategy number 2, which means we are using a linked list, and also the front of the linked list is the top. Okay, just to remind you about the implementation detail. Let's talk about push. Okay, if I have the push over here, and then of course you can do whatever implementation that's necessary. And now let's talk about ensure. Okay, let's talk about, okay, first of all, changed and also unchanged. So these are the two. Let's sketch some diagram over here. The implementation is now going to be something like this. So now let's say it's now pointing to, let's say, 3 different elements, right? It's a linked list. Okay, it's pointing to nowhere. That's the end. And then let's say, I'll just say A, B, and C. Make it even simpler. Okay, A, B, and C. And we know that according to the strategy, this is the top. And apparently, this is corresponding to this particular stack. Should be C, B, and A. Okay, this is before the push. We're going to push a new elements to it. Okay, so now, how can we do it? If I want to do the following push, let's say, if I want to say push, let's say D into the stack. Should I insert to the front or to the end? The front, right? Good. Just double check. Let's do it. So now that means now in the new version here, I still got this particular imp, and then this should be the new top. So I'll put D here, and that should be the new top. And everything else should just be the same. Let me see if I can just do copy and paste. Hopefully I can. Oh, actually, you know what? Let me just draw it. Okay, never mind. Okay, so we got A here, and then we got B here, and also we got C here. Okay, so that's kind of the pre-state and post-states, right, between the push. So now, how exactly do we specify the unchanged? Well, for the change, it's very easy. So D should be at the front. So you would say, for example, in permutation, first is just the same as the G. Whatever G you're passing to the push. Okay, change is always easy. It's very specific. What about the unchanged over here? How do you figure out exactly what to write? Any idea? Should we use a cross, maybe? If you do use a cross, let's say, but a cross from where to where? One hint you may want to consider is this, okay? Let's say indices, right, for the linked list. They are linear structures, so they got indices. Index 1, index 2, index 3, okay? And here we got index 1, index 2, index 3, index 4. If you consider the first version and it draws a similar diagram, the way you write it across is easier because index 1 in the pre-states should correspond to index 1 in the post-states. However, it's not quite the case for strategy number 2. That's why it's worth talking about. So now you can see that over here, you can see index 1 is actually corresponding to index 2 in the post-states, right? And also index 2 over here is corresponding to index 3 over here in the post-states. So they're kind of like a one-off. But how exactly do you actually specify this? Okay, I got 2 choices for you. How about we just make sure we agree with the first part? I can either say version 1 across. Let me just maybe use blue here. I can either say across, maybe from 1 until imp dot count. And then I can say across, and then 1 until, let's say old version, imp dot count. Basically, I want to use indices. Second one? Okay, let me just number them. Okay, just make sure everybody got it clear. Guys, this exercise is really worth doing. That's why I wanted to really talk about it, right? 1 and 2, okay? Would you think I should do 1 or 2? If you did 1, for example, that means you want to consider all the 4 indices, agree? Because that's talking about a new count, which is 4. If you actually talk about number 2, that means you only worry about 1, 2, and 3 in the pre-states, right? Apparently, for the unchanged part, we only worry about these 3 elements in the pre-states. So that means we only need to consider 3, not 4. Okay, that's a quick justification. Okay, so now we should really do the following. Okay, so now this is not the way to go, so we simply do that. Okay, let me write it out quickly, right? So if I say across 1 until old imp dot count, And then I say all. Okay, you can think about why we might need all. That's more convenient. Of course, you can use some. They're equivalents. So now, how should I write the body of the cross all? You want to suggest something, please?
Yeah, we could do like old if
Do I need parentheses? Why don't I try it without the parentheses? You say old imp dot, I'll say dt for deep twin. And then, what should I do?
I guess we could say is I.
Oh, yeah, I forgot to say that. Good point. It's I, let's say.
We could do
Brackets I. Let me put it like that. And then,
it should
equal to, tell that for object comparison.
Yeah.
And then,
I guess if dot equal. I mean, sorry, if at
I plus 1. Right? Any objection? Ken? You need a parenthesis. Okay, guys, please remember, in the exam, this is considered as perfect. However, in a lab test, you might just get 0 because this wouldn't compile. Be careful, okay? I'll take your question, just one moment. Okay, for the reason that I doesn't exist in the pre-state, so you have to bracket this. That's one thing, okay? If I do that, so now what you really want to know is I and I plus 1. That's actually very important. Okay, because you know that it's going to be old imp.count, so it's going to be 1, 2, and 3. And if I'm currently looking at index I, so that means I'm going to I plus 1, which is index 2 over here. So got a 1-to-1 correspondence, equivalence. Okay, that's how you write it. Ken?
Shouldn't we also go across 1 to imp.count minus 1? Because if we use old count, then it won't catch the I.
Nope. Ken actually raised a very good point. Okay. Let's see okay, Ken's concern, maybe everybody else is concerned as well. Let me rephrase your question a little bit. Here I say old imp.count, right? That's what I'm saying. You were asking whether we should actually say minus 1.
No, just not old. It should just be imp.count minus 1.
Imp.count minus 1 over here?
Because if you added an element to the end.
Okay, that's a good point. Okay. The Ken's suggestion was, should we actually say minus 1 over here? That's a question, right?
But no old. It should be imp.count minus 1 without the old.
But I'm just that version might still work.
Like this.
Let me show why this version is working, first of all, and then we'll go back to your version, okay? Let's think about why this version I initially suggested would just work. If you consider this particular old expression, what value will be cached precisely? 3, I agree. So that's going to be imp.count, right? This is the value that's going to be cached, which means in the pre-states, we have some old value over here, which is going to be assigned to imp.count, which will be 3, right? Got 3, which means simply just 3. Now, let's say when we do the push, of course, you're going to expand the size of the linked list. Is it going to change this particular integer value? That's your concern. The answer is no. There's no aliasing issue over here.
I mean, if in the implementation, it also added an element to the end of the linked list.
Nope, you wouldn't actually make a difference over here.
But how does it check that last element?
How does it check? Okay, first of all, are you okay with the fact that we'll just cache number 3 over here? Okay with that, right? Okay. So now let's say in the implementation over here, we simply grow the size of imp by 1.
But what if it also added an element to the end?
In that case, you are missing, did I actually put it? That one can be solved by a different postcondition, which we don't have to worry. Okay. I didn't really put it here. Okay, anyway. So what your concern is, what if we added more element to it? So the correct way to do it would be, we simply put it over here and say size incremented. I see your concern.
Or if you use imp.count minus 1.
Yeah, count equals,
That it would go out of bounds.
Imp.count minus 1.
It would go out of bounds for the
yeah,
old.
we'll talk about that version here. So this postcondition here is also very valuable over here because we're saying that after the push, the size of the stack is incremented by exactly 1. Okay, so that's guaranteed. When we actually use this cache value over here, it's simply going to be 3, and then we're looking at exactly the suffix of the sequence of the list over there. Okay, let me just talk about your suggestion as well. Would it work? So now, what you're suggesting is, let me write it just a header here. So this, if I simply put cross over here, 1 until, and then I can say imp.count. First of all, if I say this, is it going to work? Guys, would it work? If I change that to just this. If I say is I over here, and then if I simply use I, for example, for I plus 1, apparently I'm going to go index out of bound. Yeah, exactly. So that's my point. So here, you should really put -1. Be careful. You can either use the old value of the count, or you can use the new value of the count, -1, for this postcondition. Either way works, but I should know why. Okay, it's quite a discussion, but I think it's worth doing. Any questions about this? Any confusion? Yeah, so here, the count -1 here, when I say imp.count -1, we had to say -1 simply because imp.count is going to include the new elements and also all the old elements over here. So that you got to say -1. Otherwise, you can easily go out of boundary. Yeah, as a new element to the list. Okay, so now that's about the push, and then for the pop, you can do something similar. Okay, just make sure you're comfortable with writing such contracts. You have to really draw a diagram to show you the correspondence. Okay, version number 3, I'll just show you quickly. For version number 3, we are also going to use a linked list, but now this time the last element in the linked list will be the top, okay, rather than the front. So we just got 3 different versions for you. Okay, anyway, you can look at the contracts. So now, what's really the problem here? We're now going to criticize about this particular design, where we actually use the imp in the post condition, but the 3 versions don't seem to be very identical, right? So that means when you change from one implementation to another, you have to modify the contracts, which is part of the interface. So I updated the slides on the web, so you can look at this new page over here. So there are 2 design principles we have to keep emphasizing throughout the course. Let me just mention them the first time. The first one is called information hiding, and the second one is about single choice principle. So these 2 are both important. Okay. I briefly talked about information hiding last time. Okay. For information hiding, that means every time if you make if you think certain design decision might change later, in that case, you better hide it. That's why it's called hiding the information that might change later. In this case, you might change from array into linked list, or you might change from the front to the end, right? That's kind of like a design decision you have to want to hide, information hiding. And also for single choice principle, so that means you got duplicates in your design. In this particular case, can you tell me why do I have duplicates? Over here, let me just go back to the 3 versions over here. Duplicates in the sense that if there's a change, I have to go to multiple places to modify my design. That's what it means. Okay? So now, let's say, for example, let me just illustrate to you for this particular diagram. Okay, let's say this is version 1. Now, if I decide I want to move from version 1 to version 2, strategy number 2, how many places do I need to modify? Is it just a single place? Multiple places, right? Apparently, I have to, first of all, modify this guy here, right? Because now the end of the list, oh, sorry, yeah. So I'm circling the wrong thing, beg your pardon. I meant to show you this one. This is version 1. Let me do it again. This is version 1 over here, where we use the array, and the end of the array is the list, is the top. And now, if I decide to go from strategy number 1 to number 2, apparently I have to change this particular guy, as we said. And also, second place, we have to change the way we write the across loop. Second place, and also we have to change the way we write this across loop for the pop. So, more than one places. So that violates the single choice principle. That's point number one. Okay? Point number two. If this violated the single choice principle, how are we supposed to fix it so you will obey the single choice principle? Right? It would be very nice if somehow we can have the following structure. Okay? Somehow. Let's say this. Let's say we have our class over here called stack. Okay, we're getting to math model in just a moment. I just want to explain to you the intuition behind. Okay, so let's say we got imp over here. Okay, imp can be something, and then we got let me just make push and pop, for example, push and pop, and then ensure. It would be very nice as follows. If somehow we can introduce a new so-called abstraction function, which is called model. I'll explain what model is in just a moment. Model can be declared of some type. And what type can it be? You got to search through the MATHMODELS library. In the class, we're going to talk about sequence to begin with, but we'll deal with that later. It would be very nice if we simply define a query called model here, and then for all the postcondition, we are simply just going to rewrite it in terms of the model. Meaning that no mention of the imp. That's a critical thing. You only use the model to write your contracts. But for the imp, you don't mention that in the public view. They should be hidden according to information hiding. And then the only place you're going to use the imp is when you say model there, and then of course it's going to contain certain implementation here, and then ensure, and then n. So that's the model part. The only place you will mention imp is over here. That's the only place. Okay? We're going to see the overall structure by the end of the lecture. So now, let's say if we can get this overall structure to work. Question for you. If now I decide to change the implementation into something else, okay? Conceptually, if I change to maybe from array into linked list, or from linked list to hash table, where do I have to modify? Do I need to modify the ensure over here? Do I need to? The answer is no, because we restricted that no mention of the imp. So they don't depend on that. And also, do we need to modify this? Also no. The only place, the single place we have to modify imp would be only this part here and this part here. A single place just for the model. Okay? This is something you will see. Okay? Conceptually, that's what's going to happen. Let's see exactly in detail how it's going to work. Okay. Let me just go back to over here. For this part here, I already explained. You can look at that. Okay, just more explanation about why the two design principles are violated. So now we're going to talk about math models. Let me do one more illustration for you. Okay. Let's take a look at this example here. Let's say we got a stack. Okay, Tom, Mark, and Alan. Okay, just over here. Okay. According to strategy number 1, the top is going to be at the end of the array. According to strategy number 2, top is going to be the front of the list. According to strategy number 3, sorry about that, it's a typo. Can I fix it very quickly? This is 3, sorry. According to that, it should be the end of the list. So at the implementation level, they are very different. So now the idea about a model is we want to create a single model over here to say, for the model, let me use green. The model we're going to choose to use for the stack will be a mathematical sequence. I'll explain why it's called mathematical sequence in a bit. It would be very nice to have a single mathematical sequence over here, and then we say, for example, the end of the sequence is always the top. We have a unified view. Doesn't matter what the interpretation strategy is. And then you'll always be Tom, Mark, and Alan. And then this view is going to be just the same across the 3 strategies. Okay, it's going to be the same over here And then it's going to be the same over here as well. Okay, just the same. But how can we achieve that? Emphasize again. Between different e-permutation strategies, you want to have just the same view for the model. The model is going to be viewed by the client, so it never changes. Whenever you change the implementation strategy, you only change how you actually go from the implementation into the model. That's the key. But let's see the details here. So now, number one, how do you implement the so-called abstraction function? For example, in your lab number 2, you also have to implement a feature called model. Let's say talk about a stack class, a stack case over here. Let's say currently we are talking about strategy number 3, right? Strategy number 3, let me remind you, we talk about linked list and also the end of the list will be the top. Okay, let me remind you. And then we're going to see how we can adapt the changes. The model itself is simply just a normal function with some implementation. It's not an attribute, just a function. Okay, it's of type sequence of certain generic parameter. Okay, whatever G it is, you just use a G here. So now let's take a look at the implementation over here. Okay, let's look at that. You might do something similar for your lab number 2. Let's say, for example, since we talk about strategy number 3, so let me just copy this particular diagram over here and show it to you. How can we create that particular abstraction? Okay, so this is my implementation. Okay, that's the imp. And then when I try to execute this particular line, first of all, I create, what's the result here? What's the type for the result? Sequence, agree? Okay, result, don't forget, is simply the same as the return value. Okay, result is basically just going to point to some empty sequence to begin with. So now we are trying to go from implementation into the abstract model here. And then we're going to go across the imp over here simply as cursor. I'm just showing you across S rather than across S. You can use either one. And then, so now we're going to go over this particular linked list, go one by one. And the way we build a model from there is by simply go from left to right, because when you say across imp, it's going to go from left to right. And then every time you go there, you're simply going to call this particular command, which means it's going to update the result, right? How many iterations do we have for this across loop? 3, exactly, because we got 1, 2, and 3 here, okay? For the first iteration, we're simply going to append Allen to the end of the sequence, Allen. Second iteration, second elements, we're going to append Mark into it. Third iteration is going to be Tom. So this is our model for this current implementation. Okay? Any question up to now before we do some exercise to really emphasize your understanding? Okay, so now 2 exercises for you. Okay, the first one, I'll just mention that you should really do it by yourself. How can you write a postcondition of the model? Basically, for the postcondition, you want to draw some relationship between the return value, which is a sequence. For the postcondition over here, what's the relationship between this return value and this particular linked list? Okay, try that. They should be precision-wise correspondence. That one should be easy. Okay, I'll leave that to you. The second exercise is important. Exercise 2, and we'll do it together. What if, rather than having strategy number 3, I want to adopt to strategy number 2? Let's say. What should I change? Yes. I can, yeah, in some way, well, you basically say you can go from the end of the list and then go backwards and then append. That's one way to do, for sure. So what Alan was suggesting is this. If I go from strategy number 3 to strategy number 2, I definitely have to change this particular implementation, right? Question for you. I'll get to that. Okay, let's do that right now. Let's say if I try that over here, let me just do the following. Let me just make it very clear so it doesn't get too messy. So now, let's say we have strategy number 2, okay? Strategy number 2. Okay, in that case, I would suggest a slightly different version for you, okay? What about rather than append, I'll simply change that to prepend. Prepend is also one of the commands in the sequence class. That's something you want to get used to, okay? You can get familiar with that. This is going to work. So now by change, well, the linked list still remain to be the same type, but now we're going to strategy number 2, in which case the front is the top. Okay? Now, let me copy and paste one diagram here, and then I will illustrate the point. For strategy number 2, let me just use this diagram over here, right? For the same stack, it's going to look like something like this, right? The front of the list is the top. So now, if I adopted this particular change version, am I going to get the same model? That's the question. Am I or am I not? Or put it this way. What if I didn't change this part? If I didn't change it, what's going to happen? What's going to happen is the model is going to look like, again, result. And for the first iteration, I'm simply going to get Tom. And then second iteration, I'm going to get Mark. And in the third iteration, I'm going to get Alan. So now the green one is the abstract model, which is from the client's point of view. Is this the same as this one here? No, they are not the same. So that's not a good abstraction function implementation. So every time if you change your implementation strategy, you should really modify how you implement the abstraction function at the same time, consistently. Okay? So now what I would suggest is, okay, apparently this is not good. Okay? Let me just do this here. I can say rather than append, I can simply say prepend. If I say prepend over here, let's try one more time. Now result is going to be initially empty. And then for the first one, I'm simply just going to write Tom. Okay? And then for the second one, I'm going to prepend. So let me just move this away. And now I can prepend Mark into it. So now Mark is over here. So we're getting there. And for the third iteration, I'm going to get also Alan. So prepend Alan over here. So now this is an abstract model I have. Do I have a consistent view between implementations? I do. Because now you see Alan, Mark, and Tom. Here you also see Alan, Mark, and Tom. So what I have just illustrated to you here, the model should be the only place you try to talk about implementation strategy, right? That's the postcondition and also implementation there. But in all the other postconditions, you should use the same model. Any question about this for implementing abstraction function? In your lab number 2, what should you do? Well, what's the model here? Let me draw a little bit of connection here just to help you. In your lab number 2, think about at the implementation level, you simply got a list graph. And then at the abstraction level, which is the, I'll say spec, okay? And then over there, we got a comparable graph, I believe. Okay? Without telling you exactly how to do it, right? Basically, the model you have over there is of this type. How to implement that? Basically, you have to somehow go across every vertex or every edge and convert them into a comparable graph. That's what you got to do, okay, in the implementation. And now let me go a little bit further. Let's say there's another extra exercise for you. The list graph over here currently is using the adjacency list implementation strategy. Back in 2011, you actually got other possibility for implementing your graph, right? What's the other one? Adjacency matrix. Have you heard about it? Okay. Let's say, for example, For your lab number 2, you have to somehow define this particular abstraction function, right, to implement your model. Let's say this. If I decide to change my sequence about the graph, okay, so I will change my strategy of implementation. Rather than using a list graph, I will use maybe adjacency matrix graph using a two-dimensional matrix. So now, what I don't want to have is for any clients who depend on my graph to really change their view publicly. So now, the only thing I have to change, if I use the model in the first place, the only thing I have to change is to change how I can convert from adjacency graph into this particular model. Just change that implementation. Okay? That was something extra I want to show you. Guys, any questions? Yeah, basically for implementing this particular abstraction function here, you can do whatever you think that's appropriate. Overall, your goal is to say, I want to return a comparable graph, like a model type. How do I construct that model objects by using its appropriate constructor or features? And then the way to do it is by going across maybe some structure in the implementation level and then add them to the comparable graph, something like that. Yeah, for the details, I'll rather leave that to the office hour. I just want to talk about the general idea. Questions? No, that's not the case. You always got a single model here. If you look at this diagram here, okay, for strategy number 1, I have a single model, which is a sequence. And always the end of the sequence is the top. Okay, number 1. If I go from strategy number 1 to number 2, implementation changes. First of all, it changes from array into linked list. Number 2, the top now becomes the front, but it's only limited to the implementation level. From the model's point of view, it's still the same sequence. How can I achieve that? If I modify my abstraction function accordingly by using prepend, as I explained, the abstraction function will always return the consistent value. If that's what you're asking. Model is always the same. Implementation might change. And whenever you change the implementation, you want to make sure the model, its implementation is also modified accordingly. So the clients wouldn't get any inconsistent view. That's a question, yeah. Any other questions? Go ahead. Oh, the question was, good question. It's a little bit, the question was as follows. Let's say linked list, the same idea, okay? If I say my imp is actually linked list, when I say across this particular imp, so there is a design pattern there called iterated pattern. That will be the next topic after the math models. It's guaranteed. For linear structure, you always go from left to right in the collection class. Yeah, if that's something you're wondering about. It's guaranteed. You can take it for granted. Mm-hmm. Okay, so now we talk about half of the story. We talk about how you can define the abstraction function itself, like related to your lab 1, lab 2. The second half of the story is once you have defined the model, how do you use it? Okay, that's the second part of the story. Let's talk about it. Because for your lab number 2, of course, you have to use model in everywhere of the postcondition for other features, right, or precondition. Okay, let's talk about the second half of the story. So now let's see this. Let's say in the stack class, now we declare our model to be sequence, okay, and it has been implemented properly. And now let's talk about push only, just push. And then here for the postcondition here, let me read it to you. Okay, and then we have to trace it a little bit to see what exactly it is trying to say. It's saying model in the post states, there's no old, is the same as the old version of the model in the pre-states. Appended, notice that this is not the same as append. They are different. Okay? In the MATHMODELS library, in almost every class, like a relation, function, or even graph, whenever you got a command, you always got another version called the query version. For example, I'll mention very quickly. The append is a command. It does not return anything. On the other hand, appended is actually going to return back to you a new sequence. The new sequence is going to be exactly the same as the context object, the sequence over here, except that G is appended to the end. Okay? I just want to tell you there's a difference between command and query for a feature. Okay? Now, let's see, before I try to trace this for you, I want to ask you two questions. Okay? Two questions. Question number one. If I only give you this particular view, just this view over here, can you actually tell me which strategy did I adopt for the stack? Is it possible for you to tell? No. Remember the principle we said? We don't mention about imp anymore in all the contracts, in other features. We only mention imp in the model contract itself. Okay? It's a very important question for you to note. Okay? The answer is no, because no mention of imp in the postcondition. Okay? And now, of course, if we actually change the strategy, what should we change? That's already answered. You have to change the way you actually implement model over here, right? That's something we just discussed. Now, the most important job now is to understand how exactly do we check this. That's really important. I tell you what the complication is. Model over here is not an attribute. It's actually a query. It's returning something, which is quite different from the accounts that we talked about in the previous lecture. In the previous lecture, account is simply just an array of attributes, right? But now, model is not really an attribute. It's like a function that returns something. So that's something we want to trace. Okay? Before I start tracing this code, let me just mention something to you. Okay? You can see for this particular postcondition for the push, you mention model twice. Okay? So this is one call to model, which is a function in the post states. Okay? And this model here, because it's associated with the O keyword, so this is a separate call to model in the pre-states. Okay, that's one thing you want to keep in mind. So they are simply different calls to the same function. One is in the pre-state, the other one is post-states for caching. Okay? And you will write something very similar to this, possibly for lab number 2, something similar. Okay? So now let's see how we can trace this. Okay? Yeah, I just want to trace completely for you. Okay? And then after that, we have to cover a little bit of math background. Okay? And then I will give you the assigned exercise for birthday book after that. Okay, let's see how we can trace this quickly. Okay? Let's say we start with this particular implementation. Let's say we talk about strategy number 2. Remember, for strategy number 2, we have a linked list, and then the front of the list is the top of the stack. Okay, remember that. Okay, so now this is the linked list in the pre-states, and we want to push. Okay, so now thinking this way, let's talk about implementation change first. Okay, after push Jim to the front of the stack, what we will have is something like this. So I can simply just copy this guy here, and I can just draw another one. So in the post states, which I'm going to put over here, Alan, Mark, and Tom, so they remain the same. Except that I'm going to have Jim. So Jim is now going to be somehow inserted to the front of the list, right? So that will be Jim. And this is the top. I haven't shown you any math model just yet. Okay, that's the pre-state and post-states. The only thing that's not exactly precise is I'm showing them a separate list, but they shouldn't be, right? They're the same list, but just for illustration, it's easier to show this way. Okay, so now what I want to show you now is how are we going to check this particular post condition? Okay, this one here for the push. Okay. When I look at this post condition here, I can see that this is an O keyword, which means I, for runtime, will try to cache this value in the pre-states. So what value exactly is it going to cache, right? It's going to basically say model.deepTwin. In the pre-states, right before push is executed, it has to, first of all, get the model as a sequence, and then make a deep twin out of it. That's what it's going to do. Okay? So let's see this. In the pre-states, if I simply call model in the pre-states, well, the way we build a model is by keep doing prepend, right? As we talked about before. Okay? So it's simply going to be, first of all, start with empty sequence, and then we're going to have, let me just put it this way here, so that's easier for me to draw. We'll start with empty, and then first of all prepend Tom, and then prepend Mark, and then prepend Alan. So this is the model in the pre-states. That's how we call the model, right? That's a first call, okay? And then we have to make a deep twin over here. And remember, the reason for using deep twin is because we don't want to have any aliasing effects. So that's why we want to use deep twin, okay? So now model.deep twin is now going to be just a deep twin of this particular model. Okay, let me just duplicate it quickly. And then I'm just going to copy this. Let me put it here. And then I'm just going to name it the old model deep twin. Okay, it's going to be here. That's the first call. We make a cache value in the pre-states. Okay. And now, after the push, the implementation looks like this. How is the model going to change? When we call the model again, so this is a separate call, right? So now, if I try that, let's see what's going to happen. So now, this is now going to be the new model over here. Okay, the model right now is just going to be constructed from this particular modified implementation, right? In the post states. How would it look like? You basically, well, you start with Jim. That'll be the top of the stack, and by Tom, and then by Mark, and then prepend, also Alan. So now I want you to consider these two values over here. So this is the old model.deepTwin, and this is the model. Are they the same? They are not the same. However, they basically tell you these are the separate models. One in the pre-states, the other one in the post-states. But how should we relate them? So now we want to just do the final bits. The final bits is really where you have to spend a little bit of time understanding. So now we say old model.deepTwin, which is this guy here. If you say appended G. Now, if you call appended, the appended over here, this is something called immutable query. Immutable query. Immutable query simply means if you try to call that, it's simply going to return to you back to your new objects. One analogy here. Which immutable class have you been using in Java a lot? String. Did you notice that string is actually a immutable class, right? So now, for example, when I say string, if I have a string over here, s is equal to something. If I say s dot substring, and then I simply pass something over here, does it really modify s? It doesn't. It simply say, if I got a string over here, for example, Jim, if I say Jim dot substring, something, and then it would simply return back to me maybe another string, maybe IN, just the last two characters. So it's immutable. The same idea over here. So when you say appended in the previous slides, you're basically saying, I'm not going to modify this particular pre-state deep twin value. I'm going to just create another one. Okay, let's see that. Whatever this value is, I'm going to create a new sequence that's appended with G. Okay, I'm just going to draw that quickly. So this is my, you can think about this is the context objects that's over here. So now, if I simply append G, which is Jin, right? I'm trying to put Jin over here. I'm going to draw it over here. So this sequence here, Alan, Mark, and Tom, let me put them first. Mark and Tom. And now I'm going to append exactly G at the end, which is Jin. So now this guy here is basically the appended version. So now if I try to compare this sequence over here together with this sequence over here, they are consistent, right? This sequence over here and this sequence over here. Comparing these two sequences for equality is exactly what this particular postcondition is trying to achieve. Okay? And the reason I really try to trace it for you is because you need that for lab 2. Okay? Guys, I know it's kind of tedious to trace, but any confusion or any explanation you need further? Several things you have to know. Number one, we still use old, we still use deep twin. For sure, you don't forget about that. Number two, when you do this kind of contract, think about what's being cached in the pre-states. Okay? And number three, whenever you have multiple calls to the model, think about they are just being called in different contexts, right? One is called, for example, in the post states where the implementation has been modified already. And the other one is called before the implementation was modified. Okay? Think about this example here, right? Yes? For this particular version, it's Tom. It's Tom. Yeah. Maybe, I think Tom has been the top, right? I believe. Tom has been the top, I believe. Yes. So Tom has been the top, yes. Yeah. So there's no inconsistency here. Okay, questions? Go ahead. Yes. So, okay, yeah, are you suggesting something, if you're suggesting something for me to write, I better write it down for everybody's benefits. Okay, give me one moment. So what I will do is I'm going to copy this guy here, and then, so we're still talking about the post condition, right? Yeah. Okay, what do you want me to write?
No, I'm just curious about what the appended, that feature or whatever, what it does. Does it create like a shallow copy of it?
Oh, good question. It's going to create a shallow, it's going to create a shallow copy, that's correct, I believe. Yeah, so that's why deep twin might be necessary sometimes. So you want to get rid of all the possibility of aliasing. Okay? And if you simply put a pen over here, for example, it's not going to compile, right? If you look at the signature, let me just mention one more thing, and then we can go to the like other stuff. Okay? Append itself, if you look at the signature for append and appended in the sequence class, append simply got G of type G, doesn't return anything. On the other hand, appended, and of course they're both in the class of sequence. Okay, and then appended is going to be G over here, but now it's going to return sequence of G. So that's really critical to really understand. For the same functionality like append, we got two versions. One does not return anything, just modify. The other one returns something. This one here, for the query, this one here usually is for you to implement the abstraction function. Like a model. And this one here usually is for you to write contracts, because it can be used as an expression. Oh, contract, sorry. So now for lab 2, you just got to find the relevant features, queries or commands in the comparable graph or the graph class. Okay. Okay, any questions before I move on? Everybody's okay, right? Okay. Okay, for math model, as I just mentioned, you always got the difference between commands and also query, okay? So, already mentioned. And then, so these are just different implementation here. Let me just mention one more thing about the stack example, maybe a few more things, basically. When you look at this diagram here, it's basically showing you the following, right? Basically repeating what we have said. For strategy number 1, in that case, I have my implementation over here in the pre-states. In order to get to the post-states, I'll simply do force, for example. Okay? But now, in order for me to write the contracts for the clients in the public, in that case, the only thing they know about is the model. The clients shouldn't know anything about the imp. That's not their concern. So that's why, in order for clients to really see the difference between the old model and the new model, right? Of course, you have to specify contracts like this, like the one we just talked about. But how do you make everything happen and work well? You have to make sure the way you convert from the implementation into the model is implemented properly, the model implementation, right? In the pre-state and the post-states. Okay? That's basically what this diagram is trying to show. And the same diagram applies also to strategy number 2. Okay? That one I'll leave to you. Final remark. If you look at the final version of our stack, okay, let me point out to you. So now, if you look at version number 1, strategy number 1, we got imp, we got array, and then the end of the array is top of the stack, right? So we have to implement accordingly in the model over here. And then the only place where we talk about imp is in the ensure clause for the model, okay? To actually just to talk about what it really means for that to be consistent, okay? And then you can see now for every other feature like a make, push, and pop, all of them in their post condition, for example, you can see that you don't see imp anymore. You only got model, okay? So now one thing I want you to compare very quickly when you do the study. This contract over here, this guy here for the push, and this guy here for the pop, stay the same across all the 3 versions. So this is the same for version number 2, and if you move to version number 3, they also stay the same. So now you have very consistent view for the clients. You always use model. And the only thing you have to define appropriately is the implementation for the model. Okay, that's something we keep emphasizing. Okay. Okay, any questions? I'm done with the stack. Before I move on to the next one. Question?
So essentially, if we could try to have to change the presentation or which where push or pop and stack, right? But
Yes.
right?
That's correct. Let me highlight for you. So when you actually go ahead and change the model, change the implementation from array into linked list, for sure you have to change the implementation over here. That's for sure. Okay. And of course, for the implementation for the push, the implementation for the pop, you have to change as well. But they're all internal. No, the client wouldn't see them, so that's fine. But now for all the model contract, they are the same. Yes. Okay. Let me point out some reference to you. Okay, so we are done with the stack. The remaining job now is for me to review some math model concept for you, just for your convenience. And also to give you one exercise to think about, and then we'll finish that on Monday. Okay, we got about 15 minutes. Hopefully that's enough. Okay, everything has been mentioned. Please review and make sure you're comfortable with the concept. Okay, so that's a version number 3. Okay, we are done. Okay, so this slide here, basically, when you actually review the math model concept, always make sure go to this slide to convince yourself why the use of math model can now let us obey. Number 1, information hiding. Number 2, single choice principle. Right, it's really important. Okay, this slide here, but it has been discussed already. Okay, starting from here, it's called math review, which means I will assume you still got some recollection from 1090, 2090 maybe. If you don't feel very comfortable, I do have some materials over here for you, proposition, predicates, relation, function, etc. Review them if you feel uncomfortable about the materials, okay? Speak to me if you got any problems. So I'm going to skip this part, okay? I'll rely on you to read. I think it's pretty self-contained and not very long, so you can review them. What I want to do is to do one exercise to you. So that's kind of the programming exercise you have to do maybe for the lab test and also for your lab as well. Okay, let me just go to all the way to the end. Oh, over here, sorry. Okay, so that's the end of the math review. Okay, so now for the math models, specifically, let me talk about this class called relation and function. Okay, I'll talk about the difference in just a moment, but relation first. Relation is simply just a set of pairs. Okay, and then what I want to talk about is there's certain things about domain and range. Okay, review that, and let me just do one example together with you. Okay, I want to show you some example code over here. Okay, let me switch to the iPad. Just a moment. This is kind of, let me just go to the page I want to show you. Okay. Overridden is actually a very important feature. We'll review that today. Okay. For relation. Let me go to the test itself so you can see exactly what I want to talk about. Okay, convert versus query for the math models. This is a test. Okay, let's take a look. So I'm trying to write a unit test to show you how you can use relation and some important queries or commands. Call this test relation, and then we simply say we got R and T. So R and T, they're different relation objects at the runtime. And the relation is gonna got domain being string and the range being integer. So we're mapping from string into integer. Okay. And then we also got DS standing for domain values. And then it's gonna be a set. So relation and set, they're both math model classes you wanna also get familiar with. So now let's take a look, quick look. The easiest way for you to create a relation is by simply passing an array. So that's the array notation. Okay, you just got two angle brackets, an array of tuples. You're saying that I got 9 pairs in my relation, and A, D, B, E, and C, F. So these are the domain values, and 1, 4, 2, 5, 2, etc. They are the range value, right? The integer. Okay, that's a relation. And then I can simply also create another domain value, simply A. Okay, I'll trace together with you. Okay, just give me one moment. And now the first one I want to do is called domain subtracted. Okay, if you look up the signature for domain subtracted, that one there is going to return a relation. So it's a query. It's not a command. Okay, I'll trace that in just a moment. So you want to see what the relation might be. I can simply r.domain subtracted is not going to modify r. It's going to return something, so I can assign to t. Okay, and then I also got some comparison over here. We'll get there. And also we got domain subtract. Now I want you to compare. Look at this call over here versus this one here. You can see the first one here is returning a new relation. On the other hand, the second one here is modifying whatever relation you're calling, the context object. So that's why it's a command. Okay? Notice the difference. Something like that. Why don't we try to trace it very quickly to get an idea? Okay? So now let me switch to iPad over here. Let me just copy something over here. Okay, let me talk about this fragment of code specifically. Okay, this one here. Might be a little bit too small. Let me make it bigger. Resize over here. Okay, this one here. Okay, so let's take a look. If you look at that, we are basically saying, first of all, we are creating a relation out of an array of tuples, right? So now, the way you draw a relation back in 1090 or 2090 is like this, right? So now you're saying the following. So you're getting, let me put it here so it's easier for me. So now we got domain and we got range. So this is the domain, this is the range for the relation. And for the domain value, we got A, and also we got B, also we got C, we got D. Let me see if I can make it a little bit smaller so I can put it into one single column. A, B, C, D, E, F. A, B, C, D, E, F, right? So these are all the domain values. And then for the range, it's going to be integer, right? So now, for example, when you got A1, So now this is going to map to 1. And then A4 is also going to map to 4. And then B over here is also going to map to 2, and etc. That's kind of the relation we are creating. Are you good with that? Okay. I personally wouldn't suggest this kind of visualization. This is how you will learn in 1090, but it's not so easy to keep track. Okay? I would suggest just keep the array notation over here. Okay? Just keep something over here. That'll be easier for you to see. Okay? I'm just trying to show you a different way to trace your code. Let's say we got this guy here. Okay? Let's take a look here. If I try to trace this particular one, this line here, what does it really mean? Okay? You can think about conceptually, currently, R, when I'm creating R, R is now pointing to this particular relation, right? And now, when I say domain subtracted, I am creating a new relation. For sure, I am. Okay? The way to think about it is I'm basically duplicating this particular relation. Okay? Let me put it quickly. Okay, I'll put it in a way that's easier for me to write. A1, B2, and C3. And then A4, B5, and C6. D1, E2, and then F3. That's my relation over here, creating a new one. Okay? And then, of course, it's not called R anymore. I'm going to call it T. That's something I'm going to assign to. However, since I say domain subtracted, right? I'm sure you guys learned about domain subtraction back in 1090 or 2090, right? So what does domain subtraction really mean? I definitely want to get a new relation. But what does it really mean when I want to do domain subtraction? Well, it has its literal meaning, basically, right? So now, when I look at ds over here, right? If you look at ds, this one here is simply just, let me find out, it's simply just A. Okay? Just A. It is saying T is just going to be like R, except that every pair whose domain value is A, get rid of them. So that means T will turn out to be, I don't want A. Just like that. So that's how T is going to look like. That's domain subtraction. Okay, that's what you learned back in 1090. And for your information, you may want to look into another query over there called domain restricted. Okay, look into this. You will see they basically got the opposite operation. Okay, and then, so now, finally, if you try to trace this particular line to say domain subtract, so now this time, we're calling a command. It's not going to return another relation. So in that case, we'll simply just modify the context object R. So we'll simply get rid of this particular domain value. That's is all its associated pairs. Guys, you okay? Yeah, okay. Remember to distinguish between query versus command. That's my point. And I'll get to override maybe next time. However, I want to give you an exercise which we'll do together on Monday. Case study with birthday book. Before Monday, I would suggest you do two exercises. Number one, review the concept that we talk about for math model on the stack. Make sure you're comfortable with it. Number one. Okay? Number two, for birthday book. It's more challenging exercise over here. I'll explain what a birthday book is, first of all, and then think about what kind of math model you want to create, and think about how you can implement it. Okay, that's something we'll talk about Monday, but before that, let me give you a little bit of background. For those of you who took 2030 with me, maybe, in that case, you might know what a birthday book is. If not, that's okay. Okay, what's a birthday book? It simply stores a collection of entries. Each entry is simply person's name mapped to their birthday. For example, that's a birthday book. Okay, so you can see, for example, it's more like a mapping. You got Alan here. Alan has his birthday here, and Mark and Tom also have their corresponding birthday. That's a birthday book. Okay, before we talk about what kind of operation you may want to support on the birthday book, here's a question. How do you model abstractly a birthday book? Should you model a birthday book as a function, or should it be a relation? Function and relation are different classes in math models. You have to choose one, but not both. So here's a design choice you want to make. So before you can actually start implementing your birthday book, I would suggest think about what kind of abstraction concept you want to commit to. How about we try this quickly? Okay. Any idea? Should it be a function or should it be a relation for a birthday book?
I think a function.
You think a function? Why relation wouldn't work?
Well, because I know, I'm not too sure why relation would work, but with a function, you would make it to domain, right? Like Alan can't have two birthdays.
Okay, good. Yeah, you basically already talked about the difference between function and relation. If I chose a relation, for example, if I say the model of my birthday book, for example, it's going to be a relation. If I said that, for example, it's going to be from the string name into the birth dates, the range. If I said that, that means abstractly my client is going to understand the birthday book model as a relation. That means maybe Alan is born on both August 11 and also October 15. That's a relation, right? Each domain value may be mapped to more than one range value. That's what a relation is. So this particular abstraction object is not well chosen, so you should choose a function. Okay? Another question for you. When you say it's a function, right? I agree. Conceptually, do you know the difference between a partial function versus a total function? Jordan.
So a partial function may be undefined for
For some domain value. And total function means every string value is defined. So now, conceptually, the function we are trying to choose, do you think it should be a partial function or should it be a total function? I like your answer. If you say total, right? If you say total, for example, I'll follow your thought. If you say total, that means any string value that is of type string, of course, is a domain. So, for example, if I say model over here, and then I simply want to get, for example, nobody, for example, right? That means I'll be guaranteed to return a birthday for nobody. But it's not a valid name.
I thought you meant like Alan should always be associated with
Oh, not really. I'm just, yeah, because the domain type is actually a string, right? If you say it's a total function, then every string value should have a corresponding birthday.
Every single string value, like all.
Yeah, every single string value.
Yeah, I thought you meant every string value.
No, I'm just talking about, just total function, right? Yeah. So this is something extra you should understand. So we definitely agree we should really get a function as opposed to relation. Okay, number one. Number two, mathematically speaking, it should be a partial function because there are only certain names that exist in the birthday book. There are certain names that don't exist, in which case their birthday will be undefined. Okay, just something to mention. Okay. Okay, I think I will stop here. Think about how you might design contracts for your birthday book. Okay, and then we'll continue with that.